Today I'm going to talk about operations. I'm going to give you some tips and tricks, sort of shorten the learning curve, make it more of a learning hill instead of a learning mountain, and fix some of the common misconfigurations that I see. I don't have a whole lot of time, but still feel free to ask questions. I may reserve the right to cut you off and proceed on because I've got about 24 slides in 30 minutes. So, operations cannot fix a bad data model. Number one. So if your developers are doing something stupid, there is nothing you can do to help them. I mean, we can sort of make things a little bit better, but fundamentally, you got to get the data model right. So when I come into a customer site, first I'm going to explore their use cases, figure out how they're doing queries, how they're writing data, because from that you can get a number of reads and number of writes per second. Right? After you've got the number of reads and you got the number of writes per second, you can figure out how big is my cluster going to be? How much memory do I need per node? What's the overall budget going to be? Right? So as operations folks, you really need to get your developers to figure out what your read and write paths are going to be, and only from that can you derive, what am I going to need as far as hardware. So no matter how fast we make Cassandra, we can't go faster than the hardware, right? So if I do a read, if it's not in the CPU cache, I got to go to main memory, right? If it's not in main memory, I got to go to disk. Each of these have different latencies. So the trick to making something fast is to move it up the pyramid. The problem is that it's a pyramid. The top is very small, the bottom is big and fat. So what I'm going to do is I'm going to teach you some tricks for moving this up the pyramid, then also decreasing the latency of each of these sectors, right? Like, how can we make disk faster? How can we move more of the disk access into main memory so I'm not hitting the disk? One of the common misconceptions that people have is that we'll come in, we'll set up Cassandra, and we'll dedicate 8 gigs to the JVM heap. And people will say to me, well, I've got this server with 192 gigs of memory or 256 gigs of memory. Why do I need all this memory if Cassandra's only using 8 gigs? The reason why is that 8 gigs is dedicated to the JVM heap, and the operating system is going to use the remainder of that memory as the buffer cache, so to cache disk access. What the buffer cache is that the kernel knows that disk is expensive. Like if we're breaking things down in relative times, if a clock cycle is 1 second, we're talking eons, like literally eons for disk access. Like we are waiting hundreds of thousands of cycles in order to get something back from disk. So the operating system knows this and says, hey, you have a bunch of memory that's not being used by processes. I'm going to move those chunks of disk into main memory so that when you do reads from disk, you're not reading from disk, you're reading from main memory. This is called the buffer cache. When I'm speccing out hardware for a machine, I always tell people, buy as much memory as you can. And the reason being is that you get to cache more of your disk into main memory. So sizing, right? This is the main formula you're going to want for figuring if you're. So there's 2 ways to size. The first is by number of operations per second, if we're talking about a use case that fits in main memory, and then we can talk about latencies later. But the number of operations that a Cassandra node Cassandra cluster can push is determined by this formula. And so the way that this works is my hardware constant times my number of nodes times the number of cores per node divided by my replication factor is the number of ops per second. When I say ops per second, that's the number of columns written per second. So if I'm writing a row with 10 columns, divide that number by 10. Now, the hardware obviously has a large role in this. So and these are just pulled from my experience across many, many different customers. So about 3,000 for AWS, 4,000 for commodity SAS-backed hardware, 12,000 for commodity SSD hardware. These numbers get a 50% boost if you switch to Cassandra 2.0. These numbers also get a 30% boost if you switch to a new kernel. So if you switched to Ubuntu from Red Hat, for example, because Red Hat doesn't ship a 3.0 kernel. Ubuntu makes a big difference.
Can you state the boosts one more time?
What was that?
What are the boosts?
So it's a 50% performance boost for switching to a Cassandra 2.0 branch. So if you switch to Cassandra 2.0 Community or 4.0 DataStax, you should see a 50% performance boost. Also a 30% performance boost by switching to a 3.0 kernel. When you're sizing for latency, let's say I need all of my 99.9% of operations need to come in within 5 milliseconds. Well, you have to think to yourself, well, if I need all writes or all reads to come back within 5 milliseconds, that's automatically going to roll out mechanical disks. So that means that all of my reads need to either come from an SSD or from main memory. Okay. If you're dealing with a small data set or you have a lot of nodes, you can push it all up into main memory using the buffer cache. If you can't, then you're talking about SSDs. So the secret to tuning to an SLA is finding a cluster that allows you to get enough resources to match one of these latency profiles. Does this make sense? All right. Never, ever, 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 ever use shared storage. If you do, you will get yelled at, made fun of. The problem with shared storage is that it's not attached to the machine first, so it's going to have higher latencies. Second is that you're bound to the throughput for you're bound to the throughput of whatever your medium is, your transfer medium. So if you've got 500 disks at the end of a 4 gig fiber channel pipe, you're not going to be able to take full advantage of it. You're going to be bandwidth constrained. You're also sharing many, many disks with other people, and so their workloads are going to have an impact on your workloads. You may be able to get random read or random write performance, but you won't be able to run compaction. Compactions will fall behind. So never, ever, 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 ever run shared storage. Data model and shared storage are the number 1 and number 2 results in a bad experience when it comes to deploying Cassandra. So we've gotten, so I'm going to go through some tuning parameters. The first ones will work with both mechanical disks and SSDs, but then we'll get into some SSD-specific tuning stuff. So one of the key things to performance tuning is do less work. So one of the first things that you can do to do less work is turn off no A time and dur A time. And so the operating system and the file system are keeping track of the last access times for files. So if you're reading from these files a lot, it's going to be updating the access time in the file system. Why do you need that? You don't. Turn it off. Warm the buffer cache. So I boot up a node. It's going to have nothing in the buffer cache. The memory is going to be empty. So on boot, you want to read your SS tables out to dev null so that when you start to do reads, it's already in memory. You don't have to wait for it to come in. Avoids the cold cache cascades, where you've rebooted a bunch of boxes and now I'm hitting disk all the time and my latency has gone through the roof. By doing this, it's quite often that you'll see a machine going from doing minor reads all the time, even from SSDs, to doing no reads whatsoever. You look at the output of IO stat and they'll just, reads per second will just be 0, which is what you want, ideally. So this is another thing about buffer cache that can get you in trouble. The operating system will, so you have multiple sockets in a machine. Those multiple sockets have different memory controllers. Those memory controllers have chunks of memory that are allocated to them. You don't have a unified set of memory anymore. Now, it's possible for one CPU to access memory for another CPU through the transport mechanisms of the motherboard, but that has higher costs. So what the kernel tries to do is limit your read and write access to memory to the chunk of memory that's dedicated to that socket. The problem is that that can result in the CPU going to disk instead of going to the buffer cache. So you want to turn off that behavior. This helps it. It can't totally eliminate it, but it makes your life a lot better. Next trick is use SSDs. There's no reason to not use SSDs anymore. They're 25% more expensive, 10x the performance. You know, you're going to need fewer nodes. The nodes that you do have are going to be performing better. You're going to have lower SLAs overall. You can use fancy things like level to compaction. So when you do reads, you have to do fewer seeks in the first place. There's no reason not to. People try and skimp. What they're doing when they're looking at hardware costs is that they're looking at just the upfront cost, or just comparing SAS and SSDs. What they fail to take into account is the full picture. The full picture is with SSDs, you can have fewer machines and the latencies are going to be lower. In order to get the same behavior, you're going to have to move more of the data up into the memory, the buffer cache, with more nodes if you're using mechanical disks. And so it's just going to result in much higher cost overall. So here we get into the tuning of SSDs. So the operating system is tuned for mechanical disks. It doesn't know you have an SSD, so you have to tell it you have an SSD. And by default, it's going to ship with a lot of settings that aren't great for SSDs. So the first one is this read ahead. So that's how many seconds. So the operating system is not dumb. It knows that when you do a seek on disk, you're probably not just going to want that one page. You're going to want the page next to it, because very rarely do people just want 4K of data. So it's going to attempt to read ahead more pages in anticipation of you asking for that other seek, right? Now, if you think about a mechanical disk, when I'm doing a seek, I'm actually moving something physical. So it takes 8 milliseconds, which is an eternity. So it tries to minimize those seeks. So it'll read ahead 4 megs, 3 megs, some cases 16 megs of data for every 4K that you request. In SSDs, random seeks are free. There's no reason to do that. So you could be doing, let's say, 1 meg of true throughput, but then because of read-aheads, you're asking the disk to do 16 megabytes per second of actual throughput. So by setting this read-ahead to 8, which it should be for most SSDs, you're eliminating that. You'll see SSD seek time go from 6 milliseconds down to 100, 200 microseconds. If you have really fast SSDs, then you can possibly set it to 0, but 8's typically a good starting point. That's the number of, yeah.
What's the default, 256?
256, which is way too high. And, well, actually, so it's 256 for the actual drives. If you set up a RAID drive, like let's say you were using RAID 0 on top of this, the operating system by default is going to set it to 4096, which is just crazy town. So disable that. You want to disable it on all the underlying disks, and on the RAID volumes.
And then apply EC2 as well?
Yeah, yeah. Yeah, it makes a huge difference, huge difference. Same thing for schedulers. The disks have schedulers associated with each one. You need to tell it to use no op and no, this is not a rotational disk. So and these settings, unfortunately, are reset with the with every reboot. So you want to put that in your startup scripts. And again, you want to do this for every single drive, both the RAID volumes and the underlying disks. Compaction. It's this simple. Mechanical disks gets you size tiered, and SSD use leveled compaction. You always want to, so leveled compaction, typically, if you were to look at CF histograms, and I have CF histograms later, you'll see the first column is going to be the number of SS tables we have to visit in order to satisfy a read. With size tiered compaction, it's typically you're going to see, it'll top out at about 12 SS tables. With leveled compaction, it'll top out at 3. So with SSDs, not only is every seek faster, but you're doing fewer seeks because you're visiting fewer SS tables. So less work in general. So SSDs are a win-win-win. Unfortunately, leveled compaction requires about 50% more I/O. So if you're using mechanical disks, you won't be able to supply the throughput necessary in order to do compaction. So you'll often see compactions getting behind. If compactions get behind, then performance is going to start to degrade. You could start running into garbage collection issues. So it's just not safe unless you're in very specific cases. And yeah, and just generally, this is the best way to go. Also in 2.0, there are specific enhancements for time series data in regards to compaction. What we do is we look at the max timestamp and the min timestamp, and we decide, is there any data within this SS table that's still live? If it's not, then instead of attempting to compact it with another SS table, we just unlink the SS table, delete it from the file system. So it essentially means that you can get rid of compaction altogether if you're using TTLs. The thing that you want to do is you want to set a default TTL on your column family, because that prevents you from having a programming mistake and accidentally inserting a column or a row without a TTL, which can prevent the SS table from being removed. So that's something that's easy to do from an ops side, and it covers up bad code. So heap settings. This is another one of those things that people often get wrong. If you're running pure Cassandra, 8 gig heap, which is the default, starting with 2.0 or 3.2.5, it'll give you an 8 gig heap before it only go up to a max of 4 gigs. And this is a new one. The scripts won't do this for you, but you want to set a 2 gig new heap. By default, it's going to limit you to 800 megs. You want to set that to 2 gigs. And then if you're a DSE customer, 14 gigs for max heap, 2 gigs for the new heap. And then for Hadoop, it's going to be 10 gigs new heap. The reason why is that in Cassandra, in DSE, Solar and Cassandra occupy the same JVM. So in reality, you have 2 or 3 applications running within the same JVM, so memory consumption is going to go up. So you just want to have enough for the overhead. So monitoring, Ops Center, use it. It's going to give you historical graphs for all the information. Also going to make it so that you can automate some routine maintenance tasks. So one of the things that people often neglect to do is run repair. If you run repair, you run the risk of of data inconsistency. So if a node were to go down, Cassandra is only going to keep, by default, 3 hours of data for the node that's down. If you go beyond 3 hours, then it's just going to give up. And when you bring that node back into the cluster, let's say it was down over a weekend or something like that, then that node's going to have inconsistent results or inconsistent data. So how do we fix that? So first is the hints replication, but we're beyond that window. Second is read repair, but read repair only repairs rows that are being read. It's not repairing rows that aren't being read. And you don't want data magically coming back from the dead, let's say if it was deleted. So you run repair. Repair, what it does is it looks at the data on disk, computes it breaks it into chunks, and then computes a hash for each of those chunks, and compares that hash with its neighbor. If there is a disagreement in that hash, then it streams over the information so that you have full consistency across the cluster. Now, the problem with repair is that if you have data-dense nodes, then you're having to compute these hashes across large chunks of data. And if there's, let's say, a 1 meg difference in a 10 gig chunk of data, well, you're streaming over a large chunk of information. So you want to break that into smaller and smaller chunks. In Cassandra 1.2.8, they added the ability to run repair on subranges. But calculating the splits for all those subranges is sort of a pain in the butt. And you want to be running repair on not all the nodes at once. You want to march it slowly around the ring. So in Ops Center 4.0, we've automated this for you. So it's called the repair service. And so you want to be running repair on every node within your cluster every 9 days by default, or within GC Grace if you're modifying GC Grace. Ops Center will do that for you. Other things that you can use to monitor what's going on. So this is what I go to first when troubleshooting problems is CF histograms. So CF histogram, this is the view of what it looks like in everything prior to 2.0. In 2.0, there's changed a little bit, but the same ideas apply. So this is a histogram. So this is my units, and what the value of the unit is depends on which column I'm looking at. So in this one, it's how many SS tables I had to look at in order to satisfy the read. So I had, for 3,579 of my reads, so essentially all the reads in this example, the offset is 1, so that means just visiting 1 SS table. If it was 2, let's say I had 200 with 2, then I'd be 200 with 2 200 requests required visiting 2 SS tables, and the rest just visited 1. With leveled compaction, that shouldn't ever go above 3. If it's going above 3, then that probably means you're falling behind on compactions. With size tiered, if it's going above, you should never go above 12. If it goes above 12, then you're having trouble with compaction. And typically, it's either a data model is incorrect or there are disk I/O issues. Now, write latency and read latency, these are in microseconds. So for write latency, I typically like to see I like to see the peak of the histogram. So if we were to graph this as a distribution on a graph, I like to see the peak no greater than 150 microseconds. This is because the write path in Cassandra is constant. It's never changing. It doesn't matter what underlying storage media you're using. It's going to write to the commit log, and then it's going to update the mem table. And only after the mem table reaches a certain size, then it's going to be flushed to disk. So we're writing to memory for the most part in Cassandra. So writes in Cassandra are always fast. They're constant. They will never degrade in performance as your data grows, like it will with a B tree, like it will with MySQL, with Oracle, with Mongo, with all these other database technologies that use B trees. So if we're seeing write latencies that are super high, that means data model's bad, node's unhealthy, disk is doing something weird. So it allows you to narrow down the possibilities. Read latency is dependent on data model and how many SS tables and data on disk, so the variance is going to be higher there. For main memory, again, I like to see reads coming in at 130 to 150 microseconds or less. I mean, you can see reads as low as 36, 30 microseconds for a read, depending on how big the row is. This is excluding network latency, by the way. So this is just within Cassandra itself, getting ready to respond. For SSDs, typically single-digit millisecond, less than 5, dependent on row size. If you're using mechanical disks, it can be all over the place because a single seek on a mechanical disk, if we're talking SAS drives, is typically 8 milliseconds. It's a lot higher if you're using SATA. Also, for SSDs, the concurrency pipeline for how many requests can I process in parallel for an SSD is typically around 6. So if you go over a queue depth of 6 with an SSD, then you're going to start to see a pretty steep drop-off in performance. That drop-off in performance is even more abrupt if you're using mechanical disks. And it's just horrible if you're using SATA disks. You shouldn't be using SATA disks for the most part. SAS is really cheap, you're just going to run into a world of hurt if you're running SATA disks. These last 2 columns I use for troubleshooting data model issues. So this is going to give me my row size in bytes, and this is going to give me my row size in column count. So if you see something here, like I have a single row that's got 11 million columns, and the rest don't, well, do I have a programming bug? I had a customer, they were using Cassandra for doing spam analysis on email, and they were using a column family to keep track of what domains or the domains the email was coming from. So we looked at one of them, and they had crazy hundreds of millions of entries for this one row. And so I asked, so what is that row? And they said, it's Google. Are you going to blacklist Google? No. Then why are you keeping track of a Google row, right? Again, going back to performance tuning, the easiest way to get more performance out of the system is to do less work. So you don't necessarily need to track Google, every recipient that came from Google. So remove that row from disk, remove that row or filter it out in the application, suddenly all the performance issues went away. Because they were essentially both updating and reading from this very wide row with every email ever sent from Google or Gmail. The next thing that I like to take a look at is TP stats. So the only 2 sections that matter are this last one, this all-time block, and this section right here. So the most important one is flush writers. So you can see this one has an all-time block flush writer. Essentially, Cassandra attempted to write to disk and couldn't, so it gave up. That's probably going to be, because there is no corresponding dropped message here, that's going to be compaction starting to fall behind. So that you could be so that could be 2 things. You either could have have a compaction throttle set too high for your disk. So sometimes people take off the rate limiter for compaction, and their underlying I/O can't support that. So you want to put a throttle back on. For SSDs, I typically start out setting it to like 64 megs, or they're running leveled compaction and they shouldn't be, or they just need more I/O for what they're pushing at the cluster. They could, or possibly add more cluster nodes. The other thing is the mutation. So when Cassandra is attempting to replicate a write from one node to another, it's going to come across as a hint, right? Cassandra is going to prioritize requests that are coming from the user over requests that are coming via replication messages. Right? If the node is so bogged down with client requests that it's having trouble responding, it's actually going to drop replication messages coming from the other nodes. That'll show up here as drop commutations. Right? The only way that you're going to repair this inconsistency is through read repair and through repair, those two mechanisms. So this is why you always need to run repair. The other thing is that probably means that your Cassandra cluster is way too low. It's way too small for the amount of load that you're pushing at it, because the nodes just cannot keep up. So people always ask me what to monitor, and this is what I look for. You can set alerts for all of this in Ops Center. I'm pending for all of the people taking photographs. Yeah. Yeah. Also, in the next version of Ops Center, we're going to have an agent that sort of looks for all this stuff. For instance, you can define rules, and it'll look for misconfigurations and weird things. So, best book ever for trying to figure out like what's going on in my system. So, my favorite tools are IOStat. Really, IOStat's my favorite tool. Because almost every issue that every customer that I come into, they're having issues with I/O, so it allows me to find all the I/O issues. And the most important column in IOStat, like let's say I do IOStat space -x space 1, which is give me the extended output every second, await, because that's going to give me the latency, the average latency for the seeks for that second. And for an SSD, you want to see that less than 1 millisecond. Typically, it's going to be 0.1 or 100 microseconds or 0.3, which is 300 microseconds. Every once in a while, you'll see it spike up to 6 milliseconds or 12 milliseconds, but it should shoot right back down. Most of the time, it should be under 1 millisecond. So that's it. Questions? I'm over. So. No questions? Okay. All right. Go.
So, for example, if a read is taking time, can you give us the path that you would go through actually to diagnose? So one thing you said is you would look at the CF stats and then find out, how many SS tables it is trying to see.
Yep.
But if the numbers do not indicate anything, and your IO stat is also not like indicating like high numbers for seeking this, what are the other things you would look at to understand? And one other question is like, how would you know a particular read is coming from, in memory or it is coming from the disk?
So you can tell pretty easily based on the latency for that read. So if it's less than 100 microseconds, then the only place it can come from is from in memory. If it's taking less than 8 milliseconds, then the only two places that it can come from are an SSD or in memory. So you can take a look at that. First, and then the next one is you look at IOStat. You just watch the output, and if you're seeing reads hit the disk, then you know that it's coming from main memory. Sorry, if you're seeing reads on the disks, then you know it's coming from the disk. If you're seeing reads, if you don't see any reads, then you know everything is coming from main memory. What you can do is you can look at the throughput of your disks in IOStat, and you compare that to the throughput of the network controller. And from there, you can say, oh, 70% of my reads are coming from main memory and 30% are coming from disk. Also, in Cassandra 2.0, we keep track of the amount of hot data, and so you can get that metric from JMX and from CF stats as well, like how much of the data is hot in that column family.
Okay.
Any other questions?
Any locking issues?
So locking is is hard to track down. So you can look at Locking's hard to track down without, well, first of all, locking is rarely the issue. And the reason why is because so in a B tree, you have to lock a segment in order to modify it, right? Cassandra doesn't use B trees. And so once an SS table is written, it's immutable. So you don't necessarily need a lock in order to access it. The only time you'd ever need to lock it is if you're getting ready to do compaction or something like that. So locking is very rarely going to be the issue for read and write path. Now where locking can be an issue is between different stages in the thread queue. And there is no good way to monitor that without severely impacting the performance of Cassandra, because then you're doing profiling.
What about mem change with locking? Read and write and read?
No, it's not an issue. Never an issue. Yeah, never an issue.
There's no lock
It's there is a lock. Well, actually, so yes and no. It's using a concurrent one of the concurrent Java structures. Well, in the currently shipping releases, it's using one of the concurrent data Java structures. So it's using memory fences in order to handle the concurrency there instead of locking primitives like a mutex or 7.4 or something like that. Right. Because you had a couple of questions I want to ask. Let's mix.
With SSD, you have a certain percent is free because SSD provides the right. I mean, how much space do you have?
So if you're using leveled compaction, then I don't want to see disk utilization go above 75%. If you're using size tiered, I don't want to see disk utilization go above 50%. Other questions?
So you said that there's off-center to monitor the node, right? And off-center also creates a free space.
Yes.
So that also takes some space, or that gets replicated.
So it does take space. It does get replicated. So what it's doing is all the counters that it uses for graphing are kept in Cassandra. If you have a larger Cassandra cluster, then the performance of keeping track of all those counters can have an impact on the performance of your cluster as a whole. And so you want to spin up a small Cassandra cluster just for dumping the data. The other problem is if your ring is going down for some reason, let's say you have a massive batch of SSD fails or something like that, then what you want to, you won't be able to get to your data to see all the alerts because the data is on the Cassandra ring that's going down. So by having it on its own ring, you're going to get some additional availability.
Because what I did was just launch a 3-node Cassandra cluster and had off-center to monitor it. But then every day a few MBs just increase by its own. I mean,
yeah.
So
because it's monitoring lots of counters at essentially, I think, minute level granularity. So it's a lot of different counters and it's going to take up space. Yeah. All right.
Okay, so when I'm doing a SQL with an in class which reads like 500 rows, okay, where I say, ID 1, 2, 3, 4, and then when it actually captures the data in the CF stats, would it be, the entire in class, or is it the read per ID?
So it depends on your data model. So what I would do in this case is use tracing. So we have tracing built into SQLSH. So if you want to know why a particular query is running slow, hop into SQLSH, do tracing on, execute your query, and it's actually going to give you a big dump of exactly what Cassandra was doing and how many microseconds for each step. So you can, if you're disk I/O bound, then you can see it there. If we're having to scan through massive rows, you're going to see it there. So it's if you're trying to diagnose like why a particular read is slow instead of like the cluster as a whole, then use tracing.
Right, but from the node to state CF stats, how do I infer it's read per row or read for like a block or something like that? Whether is it like a read data for every single ID, or is it read for one single query? How is it aggregated? Well,
so you want to look at your data model. So your partition key is going to determine, how the data is accessed. So when you're creating a column family, The two most important things that you need to know are the cluster column, which is going to determine how the information is sorted within the row, and then the partition key, which is the primary key for that row. The primary key is used to determine how the data is distributed around the cluster, and then the cluster column is used to determine how the data is distributed within a row. You want to make sure that you want typically a partition key that is granular as possible and still enabling your use case. And then you want to have a cluster column that is going to be your second most used query, or is going to imbue sort properties that are important to your data model. So we're starting to get into data model specific stuff. And we're way over. We're like 20 minutes over at this point. So if you want, we can step out in the hallway, we can talk about specifics.